yeah, here, okay, so today what I wanted to do is finish up our discussion of the quantization of the free scalar field. Okay. So in particular, let me just remind you of where we left off last class. So last class we introduced, okay, how does this, no? Sorry, okay, good. Wait, there we go. So last class we were studying the field operators in the Heisenberg picture, where our basic degree of freedom is a field phi that depends both on space and time. So we'll just write that as phi of x, where x stands for the four space-time coordinates x mu. And we expand that in a basis of momentum states, or momentum operators. So in particular, we expand that in terms of raising and lowering operators. So the APs are the lowering operators that remove a particle with momentum p. AP dagger is a raising operator that creates a particle with momentum p. And here, p dot x, px is p dot x. That is a sort of compact four-vector notation. So it's p mu x mu, where p0 is, so p mu is the momentum four-vector describing a particle with momentum p and energy E sub p, which, according to the usual relativistic formula, is p squared, the square root of p squared plus m squared. So this is the formula that we've been manipulating for the last week or so. It's the basic formula that you think of when you think of the quantization of a free scalar field. For example, the Hamiltonian is something that we worked out. It just is the Hamiltonian of a bunch of harmonic oscillators, one for each momentum mode p. And then on the problem set, you're working out various generalizations of that, for example, to a charged scalar field, where you should find that there are two raising and lowering operators for each momentum mode p, one which creates particles and one which creates antiparticles. And then you're generalizing that even further, I hope, on the last problem in your problem set for a slightly more complicated field theory. So today what I would like to do is sort of complete our discussion of the quantization of a free scalar field by computing the basic observables of the system. So the basic observable operators are the field operators phi, and of course phi's are operators, and so what one would actually measure in some sort of experiment would be a correlation function of this operator. Okay. So they would be correlation functions. So things like the correlation functions of a bunch of these phi operators. So, for example, the two-point function, phi x, phi y, sort of roughly speaking, you can think of it as the observable that describes some amplitude for a particle to be created at a position x and propagate to some other position y. Here, I mean position as a point in space-time rather than a point in space. Or if you have one of these more complicated observables up here, you know, it could be a 12-point function where you have 12 different phi's at 12 different points. And that would describe some very complicated process where you have particles that are being created and destroyed at 12 different points in space-time. So these are the basic observables of the system. Essentially, these are the things that we're going to spend the whole semester computing for various different sorts of field theories. For those of you who are more interested in particle physics, You might not be interested in so much a correlation function of the sort that I've written down, but instead a scattering amplitude. You might want to care about, say, the probability that I could send in a bunch of particles with some specific momenta and charges, say, and get out a different collection of particles with a different set of momenta and charges. And in fact, as we'll see later on in this course, those observables are related in a very simple way to these correlation functions that I'm going to write down now. But for the time being, I just want to focus on these position space correlation functions. So correlation functions where we insert a bunch of operators at different positions. And we'll start by computing these in free field theory. So that's what we started doing last time, and I'll finish today, before, over the next few weeks, developing techniques to compute them in more interesting theories using what's known as the method of Feynman diagrams. Good. But before you fly, you must first learn to walk. Okay? And so we'll start by computing this two-point function in free field theory. So this is the thing that I call d of x minus y. And this is fairly easy to compute just by using this expression up here for the field operator. Okay. So this is just an integral d3p prime, where we just expand phi of x and phi of y into two sets of momentum modes, so in two sets of raising and lowering operators. And because we're sandwiching them between these vacuum states, and A annihilates the vacuum state when acting from the left, and A dagger will annihilate the vacuum state when acting from the right, the only non-trivial term that we get here is an integral d3p of e to the I, so let's say minus I p dot x plus I p dot y times the expectation value of AP times A p prime dagger. Okay. All of the other possible orderings, you know, A times A or A dagger times A, for example, will just have an expectation value of 0 when evaluated in the vacuum state, along with this normalization factor that I've written as, let's see, that would be 4 EP times EP prime. And I guess I should be careful and write a vector symbol there, although it's so small you might not notice. Good. Okay, we can then go ahead and use the canonical commutation relations for these raising and lowering operators. So what is this? This is some numerical constant times a delta function that sets p equals to p prime. That's the usual algebra of raising and lowering operators. And I can use this to do the p prime integral, and you get an expression for this two-point correlation function, or two-point function as we call it, which is the integral d3p times a normalization factor that depends on the energy of e to the minus I p dot x minus y. Good. So this is where we left off last time. And essentially all I would like to do today is spend a little bit more time getting to know this formula. Okay. So in fact, I'm not going to actually do this computation explicitly, compute this integral explicitly. I'm going to leave that to you on the next problem set. It's actually not that hard to do. There's an explicit answer involving some Bessel functions and fun stuff like that. It's not so bad, but it's worth getting to know. Instead, I just want to spend a little time sort of thinking a little bit about the physics of this formula and rewriting it in a few different ways that are going to be useful for us later on. Okay. Any questions before I continue? Good. So the first thing that I want to do is I want to consider the case where the 2 points are space-like separated. Okay. In particular, what I mean is that where x minus y as a 4 vector, so the two x and y are at the same time, so x0 minus y0 is equal to 0, but are separated by some distance r. Okay? So I've just written some 3-vector r there that describes the spatial separation between these 2 points. Okay? So this would correspond to fields that are causally inaccessible from one another. And the very first lecture I gave this class argued to you that in single particle relativistic quantum mechanics, if you compute the probability amplitude for a particle to go between 2 causally separated points, to go faster than the speed of light, you get an answer that was non-zero. And I made a big fuss about that and said some words about why that meant you needed to have particles and antiparticles. So the very first thing you might want to say is, well, okay, here I have this 2-point function. What happens when I compute it in this region? So let's go ahead and compute it. So d is now a function only of r, the distance between the 2 points. So what will it be? It'll be the integral d3p divided by this normalization factor. So I'm just rewriting that expression up here. And then it's an e to the I p dot r. Okay. And then, as we did in our earlier computation, we can just go to a coordinate system where r points in the z-hat direction. Okay. And then we can do this integral by going to polar coordinates. So we get an integral. So that integral over the 3-vector p becomes an integral first over the length of the 3-vector. So it's a p squared dp over 2ep. And then we have an integral over an angle theta, which is the angle the p vector is off of the z-axis. So that was an integral from -1 to 1 of d cosine theta. Or if you think about this in terms of the more familiar coordinates on spherical coordinates in 3-dimensional flat space, that's an integral from -pi/2 to pi/2 of sine theta d theta, okay, which I've just written as an integral d cosine theta. And then you have this e to the I pr cosine theta, which is just p dot r. And then we had a phi integral, which just gives you a factor of 2 pi, because everything is independent of phi. And then I had some 2 pi cubed numerical factor that I was ignoring, or that I hadn't written down yet. So we can then go ahead and do that integral, just as we did on the first day of class. What do you get? You get 1 over 4 pi squared. Sorry, I guess it's an 8 pi squared. Okay. I'm not actually, you're going to have to do all of the numerical factors in your problem set, so I don't have to be too careful about them. But you get a 2 pi squared, and then you get an integral from 0 to infinity. When you do the integral d cosine theta, what do you get? So you get a dp over 2 ep. So ep is the square root of p squared plus m squared, where p was the length of the momentum vector p vector. You had a p squared here. And then when you do the theta integral, what do you get? You get an e to the IPR minus e to the minus IPR divided by IPR. Or just simplifying everything out a little bit, you get minus I over 8 pi squared r times an integral dp, and you have a p over the square root of p squared plus m squared. Integrate, and you integrate from 0 to infinity e to the IPR minus e to the minus IPR. But we can rewrite that as an integral from minus infinity to infinity of e to the IPR, just as we did on the first day of class, using the fact that p dp divided by p squared of p squared plus m squared is invariant under p to minus p. So you can just relate this first term to that second term by a change of variables. Good. So this is exactly the sort of manipulation that we did on the first day of class. So does anyone remember, how should we proceed now? Anyone remember what we did to do this integral on the first day of class? We can then go to the complex plane. Okay, this is a trick that you should get used to. We're going to use it again within the next 20 to 30 minutes. You go to the complex plane. In particular, you note that because of this e to the IPR factor, this means that the integral is highly convergent in the upper half of the complex plane. In particular, that integral, so we're doing an integral along the real p axis, but you can always deform the contour of integration to go to the upper half complex p plane. And if the integrand were an analytic function of p, then that integral would just have to be 0, because you could deform the contour all the way to where this exponential factor went to 0. But the integral is not analytic. You have that branch cut coming from the square root of p squared plus m squared. And so the only contribution that you get to the integral comes from the integration along that branch cut. And that branch cut, so you have a branch cut from p equals im to infinity, and then you can integrate along that branch cut, and you get an integral from m to infinity p dp of e to the minus, here, let me call rho ip. So you can write this just to make it clear that everything's rho. Actually, here, everything's real. Everything's not rho. Everything's real. So let me write p as I rho. And then you can just do the change of variables from p to rho and write this as an integral d rho. You get an integral of rho d rho over the square root of rho squared minus m squared, integrated from rho going from m up to infinity of e to the minus rho r. Okay. So this is a perfectly nice integral. It's an integral that you're going to compute explicitly on your problem set. But rather than dwelling too much on the exact form of the answer of this integral, the point that we want to make is that just as in the case of the first lecture of class, this is non-zero. And in particular, it is very small, so it falls off exponentially with r at large R. But it's non-zero. So what's going on here? You know, did we just waste the last 3 weeks of our lives by trying to develop a theory of relativistic quantum mechanics based on fields, only to discover that you can still go back in time and kill your grandmother or grandfather, depending on, well, okay, not going to, depending on your personal preference. Okay. So what's going on here? Okay, we seem to still be confronted with something that at least naively appears like a violation of causality. But in order to understand why it is that we really don't have violations of causality in quantum field theory, I want you to remember some basic facts about quantum mechanics. So in quantum mechanics, so let's imagine that we have some quantum system, and the system is divided into there's two different observables in a system, and you want to manipulate one of these observables to send a signal to your friend who has access to another one of these observables. Okay, so let's say I'm here on Earth and you're over in Alpha Centauri, and we both have some observables that we have access to that we can observe and manipulate, some operators, and I want to send a signal to you in Alpha Centauri. Okay. Well, if two observables commute, then they have separate values and the observation of one cannot influence the observation of the other. So the prototypical example might be the positions of a particle in the x-y plane. The x and y observables commute with one another, whereas the x and px observables do not. Okay. So if you really want to violate causality, what you need to do is send a signal faster than the speed of light. So in order for that to be the case, we need not just that the two-point function is non-zero, but that the commutator between these two observables should be non-zero when the points x and y are causally separated. To say that slightly differently, what I was computing up above was a two-point function of phi x, phi y. And I told you that, loosely speaking, phi is an operator that creates a particle at a position x. So that means that the two-point function phi x, phi y could be interpreted as an amplitude to send a particle from x to y. But it could also be interpreted as an amplitude to send a particle from y to x. And those two things can sort of, and so there's not a clear interpretation of that two-point function as either one of those or the other. The thing that you need to study if you really want to send a signal faster than the speed of light is this commutator. And what is this commutator? So let's just go ahead and study this commutator. So what is that? Well, that's d of x minus y minus d of y minus x. Or, to write that out a little bit more explicitly, it's an integral d3p over 2 pi squared, 1 over 2 ep. So now we just have that factor we wrote down above, an e to the minus I p dot x minus y. And you have to subtract off the thing where you have an e to the plus I p dot x minus y. So the same thing with x and y reversed. And this integral does not obviously vanish, okay? But in fact, when x and y are causally separated, this commutator is equal to 0. So d of x minus y is equal to d of y minus x. What's that? Are causally separated. So, yeah, by causally separated, I mean that the 2 points are not in causal contact. Okay? So spatially separated, but at equal times, for example. I understand, yeah. So acausally related might be also the language that sometimes people would use. Okay. So the commutator is equal to 0. Okay. So there are a variety of different ways of seeing this. Okay. So one very simple way of seeing this. So for example, in the case that we saw above, where x minus y, so where the 2 points were only spatially separated, this 2-point function was a function only of the distance between the 2 points. And in particular, it was a function of the absolute value of the distance between the 2 points. It has to be, right? That's just rotational invariance. In particular, if you think of 2 points on the xy plane, there's a rotation about the z-axis that would relate, a plus r separation to a minus r separation. So the fact that physics is rotationally invariant means that these two guys have to cancel. And more generally, for any two causally separated points, there is a Lorentz transformation, that is to say, a symmetry of special relativity that interchanges x and y. Now, next week, actually, I'm going to give you a brief review of some facts about special relativity. But if this is not clear, you can just remember that if you have any 2 points that are causally separated, so they're outside of each other's light cone so that you can't send a signal from one to the other without going faster than the speed of light, then there's always a reference frame where those two events are simultaneous. Okay? That's the relativity of simultaneity, right? You can always, if you have two events which are not causally accessible from one another, then you can always find a reference frame where they're simultaneous. And then you could use the argument that I gave above, that there was some rotation that interchanges the two. So that's a sort of slick argument. What I'm going to do in a second is describe a sort of much more well, I don't want to say it's less slick because it's also sort of slick, but a somewhat different way of computing these 2-point functions. But before I do, let me pause and see if there are any questions. Any questions?
We get the physical interpretation of this 2-point function. I guess if you have, say, phi y 0, then you take the Hermitian conjugate, then you get a dagger.
Remember, phi is a Hermitian operator. So, right, phi is an observable. Okay, remember in our stupid mechanical model of balls on springs, phi is literally the vertical displacement of a ball on a spring, something you can observe. And anything you can observe when you quantize a system becomes a Hermitian operator, right? That's the basic rule of quantum mechanics, that observables are Hermitian operators. So phi dagger is equal to phi.
So for example, in the problem set we are doing.
In the problem set that you're doing, you're treating phi, you're taking a complex field, okay? So that would correspond, that's just, as you showed originally, a fancy way of rewriting. It's a fancy way of packaging two Hermitian operators together into an operator that's not Hermitian. Let's put it that way. Like you could always take a Hermitian operator A and a Hermitian operator B and take the operator A plus IB, okay? Then that's a collection of two Hermitian operators into one non-Hermitian operator. And you called that non-Hermitian operator phi, where phi you think of now as a complex scalar field. Good. Hopefully that, yeah, more or less clear. Good. Question?
Maybe it would be a little bit misleading now, but so if we have two states that are in tangent, let's say, and we have two operators that measure observables in these states,
Yeah.
then is there a nice argument about this when we have a tangent?
Okay. Remember, you can't send signals using entanglement. The vacuum state, empty space, right? The reason, I mean, that's an excellent point, right? So what does it mean that phi of x, phi of y is non-zero? So d of x minus y was non-zero. What does that mean? These phi's are observables that are located at different points in space. And this correlation function literally says that these observables are correlated. Okay? But it does not say that one of them is causing the other, right? There's a difference between correlation and causation, right? You can be in a state where different observables are correlated, okay? But that does not mean that one of them causes the other, right? my blood pressure and the value of the stock market are correlated, but only one of them causes the other and not the other way around. Actually, I don't really care about the stock market. I don't know why. Yeah, the age at which I can retire and the stock market are correlated, but only one of them causes the other.
So this e to the minus mr says something.
Right. Yeah. Okay. Sorry. So what does this e to the mr say? Okay. This e to the mr says that the vacuum state of quantum field theory is some highly entangled state. When you think about it in position space, the vacuum state is a highly entangled state. There's tons of correlation between observables at different points. The reason, a fancy way of saying why we go to momentum space is that the vacuum state of a free field theory in momentum space is not entangled. It's just a product of a bunch of vacuum states. And so correlation functions in momentum space don't have any of these funny properties. Correlation functions in position space do. So if you haven't thought a lot about entanglement, don't worry too much about it. But yes, that's a good way of thinking about these sorts of things. It's an important lesson. Even the ground state, the vacuum state in a free quantum field theory is a highly complicated beast, right? There are correlations present between different observables, even though these observables cannot physically affect one another. That's actually a good way of restating what I was saying earlier. Excellent. Other questions? Yes.
If we deal with masses, we get zero for...
Good. You'll find out when you do the problem set next week. Okay. So yes, it turns out that the correlation function for a massless field, it has a different behavior. It falls off. Well, you'll find out next week. If you remember that electromagnetism is described by a massless field, the electromagnetic field, then you should be able to guess more or less how that correlation function behaves. Good. Any other questions? Good questions. Great. Okay, so what I'd now like to do is I'd like to present an elegant trick for writing down correlation functions in momentum space. And this trick is really motivated by the observation that when we write down, say, this two-point function, so here is my expression for the two-point function right here, d of x minus y. That's not something, so the thing that I'm integrating here is a 4-vector dotted in with another 4-vector, so it's a nice sort of Lorentz invariant looking thing. But I'm integrating only over the spatial momenta, not over 4 momenta. And what I'd like to do is write this in a way that's a little bit more manifestly Lorentz invariant. In other words, I want to treat space and time on equal footing. So if I'm integrating d3p over the spatial momenta, then I should also try and find a way of writing this where I can integrate over momentum and energy at the same time. Okay? And so there's a lovely little trick that one can do, which we're going to be using a lot in this course. So I thought I would just take a few minutes to explain it in a bit more detail. So remember that this correlation function, let me just rewrite it for you here, was integral d3p 1 over 2 EP times e to the I p, maybe there's a minus sign, dot x minus y. Now, what I want to do is I want to look at that factor there, that 1 over 2 EP. So that's 1 over twice the square root of p squared minus m squared, or plus m squared. And, yeah, now, this is just a really dirty trick. What I want to do is I want to notice that I can think about this as the result of a contour integration. So in particular, what I want to do is I want to think of the function 1 over p squared minus m squared, okay, where p squared is now the 4-vector squared. So p squared is p mu, so that's p0 squared minus p vector squared. And so what is this 1 over p squared minus m squared? That's 1 over p0 squared minus p vector squared minus m squared, which I could write as 1 over p0 minus ep times p0 plus ep, because ep is the square root of p vector squared minus plus m squared. And so then I could think about p squared minus m squared as a function in the complex p0 plane. And it's a function with two poles. It's got one pole at minus ep and another pole at plus ep. Right? That's why I wrote 1 over p squared plus m squared in this form. It has two poles, one pole at p0 minus ep and the other, one at p0 equals ep, where this term diverges, and one at p0 equals minus ep, where this term diverges. And so what is 1 over 2 ep? Well, that's the residue of the pole at ep. In particular, if you did the contour integral in the p0 plane, where you just integrated around this pole here, you would just pick up the residue. So we're integrating 1 over p squared minus m squared. And you pick up the residue at p0 equals to ep. And the residue at p0 equals to ep is just this quantity here evaluated at p0 equals to ep, which is 1 over 2 ep. So this is just a sort of dirty trick for taking this factor that I wrote here and writing it in as an integral over p0, which will allow us to write our two-point function in a way where we integrate d4p rather than d3p, integrating over p0 as well as d3p. So for example, let's imagine that we were computing this commutator that I just computed for you above. So that was 1 over 2 ep times e to the minus I p dot x minus y minus e to the plus I p dot x minus y. So let's just imagine computing that integral. Well, let me just rewrite this a little bit to make it clearer. So let's write this as an integral d3p over 2 pi cubed times e to the minus I p dot x minus y over 2 ep, where in this expression p0 is equal to ep, as we defined it earlier. But then we can rewrite the other term as e to the I p dot x minus y divided by minus 2 ep, where I've done a change of variables. And that change of variables is the one where I take p vector to minus p vector, okay? To turn that, I want a minus sign there, to turn that plus sign here into a minus sign. But then I have to change p0 to be minus ep in order for that expression to be true. And I've done that so that both of those terms have an e to the minus ip x minus y. And I want to think about them as two contributions coming from an integral over p0, where I pick up the contributions from both of those poles. Is that clear? Any questions on that so far? So to make this a little bit more clear, let's consider the case where, say, x0 is bigger than y0. If x0 is bigger than y0, then this commutator that I've written above is an integral d3p over 2 pi cubed times a contour integral dp0 over 2 pi I times, so I'll put a circle there to remind ourselves it's a contour integral, times e to the minus I p dot x minus y divided by p squared minus m squared. And what's the contour I'm going to integrate over? Well, the contour in the p0 plane, so I have two poles, and I want to integrate over a contour that goes just below the poles, like that. Why do I do that? Well, I do that because I'm keeping x0 larger than y0 so that I can complete this contour by integrating at large imaginary values of p, and then I just pick up the contributions of those two residues. And the contributions of the two residues are those two terms that I wrote here. Okay. And so there'll be a plus or a minus sign depending on which way I choose to integrate this contour. I want to think about this as an integral from minus p0 going from minus infinity to plus infinity, which means I'm going around those contours, I'm going around the contour in a counterclockwise direction, so that I actually have a minus sign here. So just to summarize, we close the contour in the upper half plane to pick up the both poles. And so this quantity that I've defined here, so let me give it a name. I'll call it d sub r of x minus y. So that's the integral. So that's I times the integral d4p over 2 pi to the fourth times e to the minus I p dot x minus y over p squared minus m squared, where we integrate over the contour, where we integrate over the contour just below the poles. So that's a definition of a propagator. And when x0 is bigger than y0, so that we can close the contour in the upper half complex p-plane, this quantity that I've written down is just a commutator. So what happens if I have x0 less than y0 instead of bigger than y0? Well, in that case, I can close the contour in the lower half complex plane. There's no poles there, and so I'll just get 0. So this quantity that I've called d sub r is just the commutator times a theta function, which is 0 if x0 is less than y0, and 1 if x0 is bigger than y0. And I've given I call this d sub r because this quantity has a name. It's referred to as the retarded Green's function, or the retarded propagator. And it actually has a very important and interesting physical interpretation, which I'll describe to you in a second. But before I do so, I want to pause and see if there are any questions. So I'm doing a little bit more of this mucking around with contour integration. And really, it's really to make these expressions that I've written for these propagators as simple as possible in momentum space. In anticipation of the fact that at the end of the day, Life is going to be much simpler if we work in momentum space instead of position space. And what we see is that basically this propagator is 1 over p squared minus m squared when we write it in momentum space. Any questions? Is this more or less clear? I mean, I'm assuming that most of you have seen some sort of complex variables before. How many of you are mystified by these complex variables? Let me rephrase that. Nobody will raise their hand if I phrase it that way. How many people are not mystified by complex variables? Okay. If you're those of you who are not mystified by complex variables, you may want to just like it's actually all of this mucking around with contours is really very simple. Like it's really nothing complicated. You just probably want to go through and find a nice book on complex variables, and remind yourselves or learn a little bit about what a contour integral is and what the residue theorem is. That's all that we're using here. Okay, you can go to the Wikipedia page and learn it in an afternoon, most likely. Good. Any questions? But the basic point to keep in mind is that what we're doing here is we're working in momentum space and pointing out that when we write things in a manifestly Lorentz invariant way, the propagators look incredibly simple in momentum space. In particular, they're this function 1 over p squared plus m squared that has a simple poles at p0 equals to plus or minus EP. I mean, it's kind of amazing if you think about it, because just to wax poetic for a second, what we started out doing was we started out considering a sum over states where we're summing over all possible physical free momentum that one of these particles can have. And then we're writing it as a sum over possible 4 momenta. Okay. Now remember, the possible values of 4 momenta, so for a physical particle, I mean this is kind of an important point. A physical particle has a 4 momentum that's where the energy is related to the 3-vector momentum by, the energy is square root of p squared plus m squared. Okay. But suddenly we've written this propagator in a way where it looks like we're integrating over all possible momenta, including those where the energy is not equal to the square root of p squared plus m squared. So it's like we're summing over things that don't solve the equations of motion. Remember, the fact that p0 is the square root of p squared plus m squared was the equation of motion, right? So it looks like when we have this propagator here, we're including things that don't solve the equations of motion. So this is one of the deep lessons of quantum mechanics, that if you think about the amplitude for a particle to get from here to there, it doesn't just go on the course that solves the equations of motion. It goes on all possible paths through space. Okay? And so what we're doing here is we're seeing a sort of manifestation of that, where you're integrating d4p over all possible momenta, including those that wildly violate the equations of motion. But the equations of motion are still present in our formalism by the fact that the propagator has a pole at those 2 points. Those 2 poles are the place where the particles, where you solve the equations of motion. When we get to Feynman diagrams and virtual particles and all that stuff, this will be very, very clear, where you'll have quantum mechanical processes where at intermediate states that you don't observe, you can think about it as a process where you don't solve the equations of motion. Good. Any questions? All right. So maybe I'll make one comment about the utility of this propagator. So first of all, it's called the retarded propagator because it's non-zero only when x0 is bigger than y0. So you should imagine it as a propagator that's relevant it's only non-zero if if the event y happens before the event x. And in particular, dr is a Green's function for the Klein-Gordon equation. So what does that mean? That means that if you think about dr of x and y, and you hit it with the Klein-Gordon operator, So here, these derivatives are d by dx's, not d by dy's. So d by dx mu, not d by dy mu. So what is that? Well, let's use this lovely formula that we just derived up here. So it's I times the integral d4p over 2 pi to the 4th. And when you hit the derivative on an e to the ip dot x minus y, what do you get? You just bring down, every time you have a derivative, you bring down a factor of ip. So you get minus p squared. Okay, did I get the Klein-Gordon equation wrong? There's a minus here, right? I always forget. Yes, because that's the signature I'm working in. Sorry about that. Minus p squared minus m squared over, oh no, oh god, I'm in that signature. Sorry about that. P squared minus m squared times e to the I p dot x minus y. You'll soon discover I'm really bad at things like sines and factors of 2. Well, you've probably already discovered that. And so, of course, that numerator and denominator cancel, and you get minus I times the integral d4p of e to the I p dot x minus y, otherwise known as the 4-dimensional delta function that sets x equals to y. So for those of you who haven't seen Green's functions before, this is the definition of a Green's function. Okay? So for example, when you solve electromagnetism, if you have some charge density present and you want to find the electric potential, which solves the Poisson equation in the presence of a charge, the first things you do is you find the Green's function for the Laplacian, and then you take your charge density and you integrate it against the Green's function in order to find the electric potential. In the present case, this is the Green's function for the Klein-Gordon equation, which is the equation of motion of the scalar field. And this can be used to find solutions of the Klein-Gordon equation in the presence of sources. So in particular, let's imagine that we were not studying the free scalar field as we have so far, but we were modifying it in some way. So here's our Lagrangian for the free scalar field. And let's imagine that we added another term to the equation of motion. That looked like that. Or sorry, another term to the Lagrangian. That looked like that. So what does this look like? Okay. Remember that anything that doesn't have derivatives of phi is interpreted as a potential, right? And so if we think about our little mechanical model for a scalar field in terms of a lattice of balls connected by springs, then what does this mean? This means that we're adding an additional force on one of the springs. Okay. So for example, if j of x is a delta function at a particular point, then that just says that you're basically hitting one of those springs with a hammer or something like that. You're perturbing the system. How is this reflected in the equations of motion? In the equations of motion, now the scalar field will obey the usual Klein-Gordon equation, but now you'll have a j of x on the right-hand side. And in your mind, you should compare this to electromagnetism. So in electromagnetism, as you saw last week, if the Lagrangian of electromagnetism is 1/4 f mu nu, but if you want to couple your field, if you want to include some electromagnetic sources, you include the current 4 vector, and you add it to the action like so, so that the equations of motion then become something like d mu F mu nu is equal to J nu. And so you should think of this Lagrangian and this equation of motion up there as just a very simple version of that for a scalar field rather than for the full electromagnetic field. So given our expression for the retarded Green's function, we could then go ahead and solve this equation. So the solution to the Klein-Gordon equation in the presence of sources just says that phi is equal to I times the integral d4y j of y times this retarded Green's function x minus y. Okay. And you can check that indeed this is a solution to the equations of motion, the equation of motion that I've written here. How do you do that? You apply the Klein-Gordon operator for the variable x. That hits this retarded Green's function over here, and you get minus I times the delta function. You use that to do the y integral, and you get a j of x. This is the usual story. This is what Green's functions do for a living. They're things that, if you have a linear differential equation and you add a source, they're the things that you use to find the solution for a general source given a delta function source. So just to summarize, the retarded Green's function describes how a source inserted at a particular point y will propagate throughout space-time using the Klein-Gordon equation. And it's called the retarded Green's function because it describes the propagation forwards in time. There are other Green's functions you could define. For example, you could define an advanced Green's function, which would describe a propagation backwards in time. That's not something that violates causality. It's just some sort of formal solution to the equations of motion that would describe some complicated field configuration in the far past that would evolve towards some delta function at a point x equals to y. So you've all seen Green's functions before if you've taken a class on electromagnetism. You may not have seen it quite in this form. Are there any questions before I proceed? Yeah, question? No? Okay. I'd like to make one final comment about the propagator that we'll be discussing in this course. So far I've presented to you three different propagators. Okay, I've presented to you the two-point function phi x, phi y. I presented to you the commutator, and I presented to you the retarded Green's function. But there's one more kind of propagator. Well, there's at least two more kinds of propagators. There's also the advanced one, which you could figure out for yourselves. But the kind of propagator that we will be mostly using in this course is known as the Feynman propagator. And it's usually denoted df of x minus y. And it's defined in the following way. It's defined as the expectation value of what's called the time-ordered product of the fields phi x, phi y. So what does that mean? Well, the time-ordered product is very simple. It just means the expectation value phi x, phi y if x0 is greater than y0, and the product phi y, phi x if x0 is less than y0. So that's just a definition. If you want to write it out a little bit more explicitly, you could write it in terms of theta functions. So you could write it as a theta function that sets x0 to be bigger than y0, and then add a corresponding theta function where x0 is less than y0. And it's just a particular combination of these two propagators. But it's a combination that will appear all over the place in quantum field theory. And indeed, it really appears all over the place in quantum mechanics as well. And at this point, I don't think there's an easy way of understanding why this particular propagator is the one that's going to appear. If you've seen Dyson series or path-ordered exponentials, then you've already seen this. It's responsible for what's known as path ordering in Dyson series. You probably haven't seen that before. So at some point when we discuss in more detail path integrals, I'll give you a problem where you work that out a little bit more explicitly. But for right now, you can just take it as a definition. And just as with the other propagators that we've described above, this propagator has a very simple description in terms of a contour integral. So you can think of it as an integral d4p over 2 pi to the 4th. So just as with the commutator and the retarded propagator, we can describe this as an integral d4p of the momentum space propagator I over p squared minus m squared times e to the I p dot x minus y. And the only thing that we need to keep track of is which contour we're integrating over. And the contour in the p0 plane that gives us the Feynman propagator is the one where we go below the pole at p0 equals to minus EP and above the pole at p0 equals to plus EP. So remember that when we computed, so just to make that clear, let's remember that when we computed the propagator, we had these two terms here. There was this term here, or rather there was this term here, which came from this pole right here, and we had to go to below it. And if we were trying to compute an advanced propagator, we would get this term here, and you would have to go above this pole here rather than below it. Okay. So this is the definition of the Feynman propagator. Now, I told you the whole point of doing this mucking around with contour integrals was to make some of these expressions simpler. And if every time I have to write an integral, I have to draw a little picture of which contour I'm integrating over, I'll never get anywhere. That would sort of defeat the purpose. So there's actually a simple little notation that we use to remind ourselves of the integration contour. So in particular, what we do is we write this Feynman propagator. Sorry, and I always forget my minus signs here. As an integral d4p of the propagator where you now encode the fact that you're choosing this contour by shifting the location of the poles, by adding a very small term there that we call plus I epsilon. Okay. So you just imagine taking an infinitesimally small number epsilon and adding I epsilon to the denominator of this formula. So what does the I epsilon do? So the plus I epsilon, all it does is it shifts the location of the poles. So in particular, if you just added a very small imaginary part to the denominator there, then the poles, instead of being at plus or minus EP, the poles would each get shifted by a very small imaginary amount. Okay. Now Now, of course, epsilon is a quantity that I'm just going to set to 0 at the end of the day. It's just here to remind ourselves of which contour we're choosing when we do an integral d4p. And in terms, so if you think about the complex p0 plane with those two poles there, adding that I epsilon just takes this first pole and shifts it up a little bit, and the second pole and it shifts it down a little bit, right? So you can just integrate along the real p0 line, and that's the same as choosing this fancy contour that I wrote up there. So this I epsilon business, it often confuses people at first. If you get a little confused, the easiest thing to do is just, well, the easiest thing to do is just completely ignore the I epsilon. For almost everything we'll do this semester, the I epsilons will not be important. Okay? The I epsilons become important when you start computing loop integrals, so sort of more complicated perturbative contributions to Feynman diagram in Feynman diagram language. We're going to be doing almost none of that this semester. This semester is going to be primarily concerned with what are called tree-level Feynman diagrams. And so in those cases, we almost never have to actually do any of these D4Ps. And so you almost never have to actually keep track of this contour of integration. So the simplest thing you can do if you're confused about an I epsilon is you can forget about it. Okay? And you'll only sometimes get the wrong answer. Okay? You'll very often get the right answer. Usually the rule is that you first forget about the I epsilons, and if your answer makes sense, then that means that you got the right answer. Okay? Because you're setting epsilon to the 0 at the end of the calculation anyway. But if you get an answer, that doesn't make sense, one of the reasons might be because you forgot about some funny contour choice, and then you can put the epsilons back in, do the computation, and then set epsilon to 0. Okay. Usually it's safe to set epsilon equal to 0 at every intermediate stage of a computation. It's only when you're actually bothering to do some of these momentum integrals that it becomes important. Good. Okay, so this really concludes just about everything that I wanted to say about free scalar field theory at this point. So we've so far computed 2-point functions. And it would be easy at this point to compute 3 and higher point functions in a free scalar field theory. And in fact, there's some sort of nice results there. It's something that, if I had time today, I would probably go through, but I've only got a few minutes, and so I think I'll defer that. Instead, maybe I want to pause here and sort of summarize a little bit what we've done and tell you a little bit about where we're going. Okay. So, in particular, you could certainly imagine computing, say, a 4-point function in free scalar field theory using exactly the same technique that we have been using so far. Okay. You calculate the expectation value of 4 scalar fields. You expand each one of them in terms of raising and lowering operators. It boils down to calculating the expectation value of some raising and lowering operators in the vacuum state for a simple harmonic oscillator. Nothing particularly fancy about it. You could write down the answers. You would get some answers that involve products of these sort of propagators that we've written down here. But the point is that in a free scalar field theory, there are no interactions. And so nothing really happens. All of the higher observables, these higher order correlation functions, are completely determined, and they're relatively straightforward to write down. And the reason really is that the Hilbert space we've described, the Hamiltonian that we've described, is one where particles don't interact with one another. You could have a one particle state. You could have, you know, a two particle state where you have two particles with momentum p1 and p2, say, and they'll just keep trucking along forever, and they'll always stay in a two particle state, and there's nothing that really can happen. What we really want to do in this course to describe interactions between particles is we want to take the Hamiltonian that we've been considering so far, and we want to perturb it by some sort of interaction term. So, for example, let's say that we wanted to describe a theory where particles could scatter off of one another, or where one particle could decay into another kind of particle. So that would be a good example. Let's say we wanted to study a theory where one particle could go along and decay into two other particles. So you could have one particle coming in here, and then it could go out and decay into two other particles. Then we could ask ourselves, what kind of terms would we need to add to the Hamiltonian in order to allow for that process? We know how to describe a one-particle state, and we know how to describe a two-particle state. So what kind of term would you add to the Hamiltonian that allows you to remove a one particle and add two other particles? Well, for this term, it would be some interaction term where you have some kind of, say, A p to remove a particle with momentum p, and then an A dagger, say, q1, and A dagger q2, if you wanted to add particles with momenta q1 and q2. So an interaction term that would allow for the creation and destruction of particles, you know, say that this is, I don't know, you know, some proton undergoing beta decay, okay, or something like, okay, some particle undergoing some decay. You'll need to have terms in your Hamiltonian that are not quadratic in the raising and lowering operators, but are higher order in the raising and lowering operators. So that means we need higher order terms in our theory. So for example, you know, one simple theory that we'll spend a lot of time studying, which has such interactions, would be a term, would be what's known as lambda phi to the 4 theory. So this would be a theory, so where you have an interaction term, where you have a phi to the 4th term with a coefficient that we'll call lambda. And this would be some sort of theory where two particles could come in and collide with one another, and you know, two particles could come in, collide with one another, and produce another pair of particles. And the amplitude for that process to occur will be proportional to that constant lambda, known as the coupling constant, that appears in the Lagrangian. So if you think of our stupid mechanical model where you have balls on springs, remember that we took an approximation where the potential that confined all of these balls on springs to live on the horizontal axis was only quadratic in phi. If you had some higher order potential or some higher order interactions, then that means that you would have all of these phonons, these propagating waves, would interact with one another. In the classical theory, this will mean literally that you send in two propagating waves and they'll bounce off of each other in some way. They'll interact with one another in some way. And in the quantum theory, this means that the theory will have interactions. Okay? Genuine particle production and destruction. So where we're going in this class is we're going to develop a set of techniques that allow us to study theories where we have interactions. So we're not going to be studying free theory for that much longer. These techniques, of course, are known as Feynman diagram techniques, and we'll use this to study all sorts of processes. But actually, before we move on to study perturbative physics and Feynman diagrams, we're going to spend the next week or two studying a different set of theories. Okay? So far in this class, we've just considered what are known as scalar field theories. Okay? These are the simplest quantum field theories, where your degree of freedom is just a number per point in space-time. Starting next week, what we're going to do is consider spinors. So we'll study theories where you have more complicated degrees of freedom that describe particles with spin, such as spin 1/2, like the electron or the positron, spin 1, which is the photon. We'll stop at spin 1, but of course, one can construct theories where there are more complicated types of particles as well. So starting next class, I'll begin with a review of some features of special relativity and Lorentz invariance, and then use that to go on and discuss the Dirac equation and spinors. And then only after that will we come back and develop the theory of Feynman diagrams. So maybe just for my information, how many of you have seen the Dirac equation in a quantum mechanics class? Okay. You have. Okay. So I probably won't review the single particle Dirac equation, but I'll derive it, but I won't discuss it in the context that you did in your quantum mechanics class. How many people feel totally comfortable with Lorentz transformations and with, okay, right. How many of you know what a Lorentz transformation is? Good. But you probably could use a little bit of review. Okay. Like, for example, today when I use terms like space-like and time-like, you feel comfortable with that? More or less? Okay. So I won't do a ton of review, but I'll do a little bit of review. By the way, one of the problems on your problem set for next week is a kind of review of the representation theory of SU2. That's something that you guys have all learned in your quantum mechanics class. But I discovered last year when I taught this that many people didn't really understand it. And so it's really important. You can't understand spinors without understanding what representations of SU2 are and stuff like that. So one of the problems is going to be a bit of review on that. And you can't even really understand what a particle is until you understand some of this stuff. Maybe I can ask one other question. How many of you are familiar with what a representation is of a group? Vaguely. Okay. So you don't need to know that for this class, but I'm going to have to explain a little bit of that language, and it's all language, it's all terminology. There's not really much, there's no physics there that you don't already know. But you will have to get used a little bit to the language of groups and representations. So there's some of that on the problem set for next week, and some of that which I'll introduce next week. Good. Okay. See you guys next Tuesday.